Thank you. Welcome, everyone. Thank you for coming out. Who here has heard of Fauna? Have you guys, a couple people heard of Fauna? Okay. Fauna is just a small part of this. I wanted to talk about data consistency in general and kind of look at like where we're at today with the different data consistency patterns. As more and more enterprises transition to cloud-native microservices architectures, the challenges of data consistency become greater and greater because you have to deal with data orchestration and between the different services and maintaining consistency within an individual service. If the clicker works. No, clicker doesn't work. All right, transition doesn't work. So first I'm going to talk a little bit about what I mean by data consistency, how we think about data consistency, some of the challenges of achieving data consistency, and then what are some of the main patterns for consistency. Why does the transition not work? Somehow I broke the transition. Anyways. So when we talk about consistency, a lot of people just think of, is my database eventually consistent or am I strongly consistent? And really, there's a whole variety of, a whole different models of consistency that we need to think about. And this is because there's a lot of different problems with the consistency of my data. So if we think about all the problems that we have with consistency, it's a lot deeper than just dealing with eventually consistent data. The challenges are with things like reading your own writes. If a driver writes a piece of data, can I immediately read it back? Can I read uncommitted data? Can I get dirty reads? Read skew, non-repeatable reads. In other words, if client A and client B both read a piece of data, are they going to see the exact same piece of data at the exact same time, or is there going to be some skew of that data? Am I going to lose an update? If I have two concurrent writers that write in parallel to my database at exactly the same time, could one of them overwrite the data of, could writer A overwrite the data of writer B? Is there any write skew? Write skew is actually the hardest problem to understand and to fix in my database. Write skew is basically when I have two parallel operations that are both read a piece of data from the database in parallel, and they both make a decision of what to write, but they write different things, and they end up skewing the writes based on these inconsistent views that they end up getting. So the way we can think about consistency, there's Peter Bailey's wrote a really good paper about this. Kyle Kingsbury put it into a really nice graph. We can look at the different consistency models and see the relationship between them in this graph. At the lowest levels, we have the lowest level of consistency, such as the ability on this left-hand side of reading uncommitted data, all the way up to serializability. So what this is talking about on the left-hand side is really your transaction isolation layers. On the right-hand side is dealing from linearizability down, is dealing with single register, single partition consistency. So this is basically for a single session, when I write that particular register, do I see have an atomic operation? So that starts with like monotonic reads. Is that read consistently read A then read B? Does that always happen in the exact same order? When I write A, write B, does that write happen in the exact same order? So these all build on each other to build up to the strongest levels of consistency. So there's a lot of different ways of dealing with data consistency in the application tier. There's a lot of different models. I'm going to just go kind of highlight a couple of them. Won't spend a lot of time in detail on all of these. Distributed sagas are really common. How many people have heard of distributed sagas? Anyone heard of them? All right, they're a really popular model out there today for dealing with coordination of microservice transactions. Akka Clustering is another pattern. And so we're going to go through all these really quickly. And I think that it's useful to, when you look at all these different patterns, that we have a way of evaluating them. And the way we can do this is using kind of consistency as a lens to evaluate our different approaches. And we can evaluate the trade-offs between these different approaches. And we can also use consistency to understand what kind of problems we're going to run into by using these patterns. And one of the things I really like to think about when I'm evaluating these different consistency patterns is how much complexity does this put on the developer? So there's no one perfect solution. There's a lot of trade-offs, the plus and minuses of all of these. The best way, everyone talks about the CAP theorem. I think the best way for me that I've heard is actually Daniel Abadi talks about, really it's more than just CAP. It's this, in the absence of a network partition, I want to think more about the trade-off between latency and consistency. So I was just talking to Pat Heelan, and he said, do you want the data right or do you want it right now? So do I want an exactly consistent view of the data, or am I okay to wait just a little bit to get it right? And really, when you look at these, there's a lot of different patterns, and they're all dealing with the transactional complexity of consistency. It's just where that's happening. So first, really quickly look at patterns for AP with sticky connections. In other words, if my client always goes to the exact same session, it's going to be much easier to achieve consistency because I'm always going to the exact same service for that connection. So this provides high availability and partition tolerance. This provides, if we look at it in the consistency models, this is basically everything under the causal consistency. So PRAM, writes follow reads all the time. I can read my own writes, that type of thing. Wow. So Akka clustering is one example of this. With Akka clustering, I can basically pin a session to an actor. That actor is always going to process that session, so I can guarantee that that session is always going to be able to read its own writes. I can guarantee monotonic reads, monotonic writes. Because that same actor is always processing it, I can use Akka clustering to scale that and to guarantee that, provide some level of guarantees that it's nicely sharded across the cluster. Akka has a lot of nice patterns for persisting that actor, so I can provide high availability. What that's basically going to do is that it's going to persist my actor state to a database and allow, if that actor dies, that I can rehydrate the actor on a different node. And on top of all of these models, there's the Akka distributed data, which provides a unique data model with CRDTs. These are data types that allow you to do things like grow-only counters. They provide like monotonic merge functions, so that I have a well-known pattern for merging conflicts. So like a grow-only counter, if I add 4, 5, and 6 to my counter, it doesn't matter what order those operations happen in. So there's a lot of strengths to Akka clustering. It's extremely high availability. It has high throughput, low latency because it's all in memory. And it can be partition tolerant if I use a split plane resolver. There's a number of split plane resolvers that are out there. There's a number of weaknesses with Akka clustering. It has a limited data size. I think one of the biggest challenges, when we look at consistency models, is that there is no transaction isolation. So there's no isolation of my data. And then the consistency level really is dependent upon the backing store of what I'm using for Akka persistence for my backing store. I'm just going to skip down to AP consistency. So this is everything in the blue. This is sacrificing a high level of consistency for availability and partition tolerance. The idea is that I want to maintain availability even if the network goes down entirely. And this provides a fairly high level of consistency with this monotonic atomic views of my data. It can provide protection for recommitted, uncommitted data. So one example of this is distributed sagas. They're in the family of AP consistency. They're not entirely AP consistent. Distributed sagas basically have a central coordinator that manages the complexity of the transaction logic. And that central coordinator basically tells one or more services to complete the transaction and coordinates those transactions. So an example would be like a travel booking. The distributed saga coordinator is going to tell the car booking, the hotel booking, the airline booking to go and book a transaction. And then those services will either complete or roll back. And depending on the state of each of the services, that the coordinator then declares the transaction as either a success or failure. And it'll tell the other services to succeed or fail as well. Distributed sagas rely on my individual workers to be idempotent. In other words, I can replay them. I can make that car booking multiple times in a row and not end up with multiple reservations. The underlying workers also have to be able to compensate for failure. So they have to be able to know how to roll back in the face of a transactional failure. So this gives me a model that's effectively once, not exactly once. Because these things don't happen exactly once, I might actually do a transaction multiple times before I actually get the entire transaction completed. And so this has a number of, upsides. It's very fault tolerant because I'm using a backing log to store all the events of that distributed saga. I do have, a very fault tolerant, highly available solution. The executors for the underlying coordinator are composable, and I can come up with new workflows to tie those together. And I'm isolating all the complex code into that central coordinator. The central coordinator provides atomicity for the overall transaction, and it allows that transaction to be aborted and rolled back. The downside to this is there's a lot of downsides to distributed sagas. They provide very weak isolation. You get into this really weird state where if your coordinator dies in the middle of a transaction, and before it actually finishes rehydrating, you can get into some unsafe states. The versioning of that transaction is fairly complex in terms of, if I want to update the workflow and have like a new version of the workflow, my backing log will have to change, and how I version that. There's a lot of complexity in doing the rollback and recovery logic. And idempotency is impossible for a lot of services. So a lot of services just can't fit into this distributed saga model. So the other area I wanted to talk about is the area with the strongest consistency, that CP consistency, with global scale transactional databases. This is the strongest level of consistency in the consistency models. So if I look at, so what this provides me is serializability, right? So serializability, the difference between serializability and linearizability is, serializability is talking about coordinating transactions across multiple tables or registers, whereas linearizability is a single register or single table. So this level, what we want to talk about is how do we provide serializability across multiple tables. And the databases in this pattern provide true ACID transactions. So I have atomicity to allow for rollback of transactions. This also provides complete isolation of the transactions. So that's really what's talking about on this left-hand side, like being able to, preventing reading uncommitted data. So I'm isolating the transactions from another transaction that might be happening in parallel. And really, when we talk about these transaction levels, we're also talking about safety guarantees. What level of safety am I providing in my database? So what's the primary disadvantage up front of these? Andy Pavlo said it best. He said transactions are hard, distributed transactions are harder. Distributed transactions over a WAN network are the final boss hardness. And this level of databases are some of the most complex to deal with and build. So he gave this warning on Twitter just recently that he's seen a lot of trends in the industry of a lot of people trying to build their own distributed transactional databases over WAN. And this warning that this is an extremely hard problem. So there's a lot of databases in this space, and it can get confusing to try to understand what is the difference between all these different databases and what they provide to the application level. When you look at databases in general, most databases provide what's called a multi-value concurrency snapshot. In other words, I snapshot my data at a single point of time, and then I operate on that snapshot. And so I can have concurrent operations that are happening on different snapshots. The primary differences between these databases is in the transaction protocol. Is that global ordering done in a single phase versus a multi-phase? Do I do a pre-commit or post-commit transaction resolution? What are the levels of consistency provided? And what's the maximum scope of that transaction? Is it a single record or multiple records? And this all ties into, as I evaluate these databases and how, what is the pattern that I'm going to end up using in my application tier? Because the application tier has to be aware that when I do my operations, if I only have a lower level of consistency, if I only am operating on a single partition, that I have to then provide, in my application tier, if I only have transaction consistency at a single partition, the application tier is going to have to provide consistency across multiple partitions. And so it pushes some of the complexity back up into the application tier. The other complication is everyone says they're ACID compliant. So what does ACID compliance mean? It means that I have, the ACID compliance can be anywhere on this ACID spectrum. So, on the very left side, I have, very weak isolation levels. My scope of my transactions is a single row. I really am eventually consistent. All the way over to the right-hand side where I have a very strong isolation levels. The transaction is distributed across multiple partitions, and I have serializable consistency. So probably the other thing to really understand between these different databases is how they apply the writes. The most common approach to applying my writes is in a non-deterministic fashion. So this is traditional, like two-phase commits. Really, I'm going to roll the dice on when the effects get applied, roll the dice on what's going to happen and which effects get applied. Right? Because what happens is the coordinator is going to walk across the cluster, and it's going to determine the effects of that contention. And then it's going to, on the second phase, it's going to tell the partitions if they succeed or fail. And so what actually ends up happening is very non-deterministic in the end of the day. And it requires 2 rounds of global consensus. The alternative to this is a deterministic database. So one example of this is from Fauna. Fauna uses the Calvin protocol. The Calvin protocol does deterministic commits. And the way that it does this is that when it receives a query into the database, it takes that query in, a non-deterministic query, and it turns it into a deterministic transaction. So I'm determining exactly what all the effects of that transactions are in the first phase. And I'm essentially turning that transaction into this kind of pure function that I'm going to operate over my state. And then I'm going to get a total global ordering of that log and commit that log in kind of the ordering phase. So that's the only round of consensus that I have to do across the cluster. And in the final state, I have a deterministic results that get applied to my database. So that's on the right side. If we look at the read side, the trade-offs on the read side are, do I do my read consistency with clocks? So this is like Spanner inspired, right? This is a big trend today is, Spanner inspired databases. The problem they're trying to solve is how can I do consistent reads with concurrent writes happening at the same time? So I want to be able to read, if I try to do a read using two-phase commit, I'm going to get very high latency. So I want my reads to avoid the two-phase commit. So the alternative is to choose a stable snapshot time. And how do I figure out what snapshot do I read the database at? And that's really a decision of how stale do I want that data to be. And by having atomic clocks, I can guarantee a very high level of guarantee that I'm reading at the exact right time. It's the alternative to the Spanner protocol. Spanner provides consistency without clocks. So I can do a read-only transaction that avoids the transaction pipeline. And I can do, basically, it uses a log-based total ordering to guarantee the stability of my reads. So because the Calvin protocol is doing a global ordering of all the transactions across the cluster, I can know that exactly at a particular point in time that I can guarantee a stable read. The challenge is that snapshot of when I read that data might be slightly in the future from when that node has actually seen the data. So I sometimes have to wait until that node has caught up on all the transactions and they've been applied. But as soon as that local partition has all the data, it can provide a read of that exact given snapshot without having to go through the pipeline. So looking at the pros and cons of this one, Google Spanner provides, it provides a very high level of consistency. It has relational integrity constraints. They provide, external consistency, which is the highest isolation level. They provide 5 nines of uptime. It's really a phenomenal database. The challenge is it's very expensive, it's very proprietary, and it ties you into the Google Cloud. It does have the nice feature that when I do a write to a single shard, I can avoid the two-phase commit process. So the alternative to that is a Fauna DB. So if I look at the databases today, like Spanner, Yugabyte, Cockroach, all these are using some kind of atomic clocks, hybrid clocks. Fauna is instead based upon the Calvin protocol. So it basically does a global transaction ordering with a log. Fauna is both in the cloud and on-prem. It provides temporality, multi-tenancy, has a row-level security built in from the core. It has a document model for the primary schema modeling. And the way that I query Fauna is through indexes. So each, what we call class, or basically table, can have one or more indexes, and those indexes are like a materialized view into my data. And that allows for different query patterns. So the Fauna consensus algorithm provides this total ordering to give me a level of serializable consistency. And that distributed log that's going to provide the total ordering of the transactions scales by being able to partition the log. The nice thing about Fauna, right, is the single-phase consensus algorithm provides the lowest possible global latency. Because I'm not doing two-phase commit, I'm doing a single-phase global consensus algorithm. I have a much lower latency. I can do low latency snapshot reads that avoid the transaction pipeline. And there's really no difference between multi-partition and single-partition transactions. Fauna provides a very powerful query language. So you can have a complex transaction in a single query. The downsides to Fauna are it is a proprietary query language. So a lot of people want to integrate Fauna into their legacy applications, and that's typically not the right approach, because the proprietary query language is really designed to have you rethink how I'm building my application and building a new type of transactional model in my application. So this provides a much higher. The other downside is, like other distributed databases like Spanner and Cockroach, because I do have global transactions, I do pay a higher price for my latency. And probably the primary difference between Fauna and Spanner is that Fauna you always have to pay the cost of a multi-partition transaction, right? Spanner can actually avoid two-phase commit with a single shard partition, so they have a lot of tricks they can play with that. Because Fauna uses a global log for its total ordering, I'm always paying the cost for multiple partition transactions. And then the final thing is temporality. Right? This is one of the really very interesting and unique aspect of Fauna, is that it maintains the evolution of data over time. And so I can basically look at any snapshot in time and understand where what the data look like at that particular point in time. This is very useful for being able to do something like give me all the reads since a particular point in time. So I wanted to do a quick demo. I'm going to put this down. Can I just hand this to you? Thank you. All right, so I have Fauna running here in the background. I'm going to run a process. This is the Northwinds data set from 20 years ago, customers and orders. This is going to load my data set into Fauna, all my customers and orders. Oh, wrong screen. Thank you. Sorry, guys. Can I really quickly turn on mirroring? Cool. So that's loaded the database. Now I'm just going to show some example queries against that database. So Fauna has a shell that allows me to connect into that database. So I say Fauna shell Northwinds. This puts me into command prompt where I can operate queries against the Northwinds data set. This is using I built a little workshop. It's out on my GitHub Retro Ryan on Fauna. So I can use this to query the database. So I've loaded all the customers. So for example, I have an index called orders by customer ID. So if I look at that index, the source of that index is the class order. Classes are tables in Fauna. Terms are the fields I want to search on. So I want to search on customer ID. And the values I want to search on are the values that are going to be returned out of that index. Like I said, it's a materialized view. So I'm providing the values that are actually stored in the database. So in this case, I'm only going to be returning order date and order ID. I could do something like return a ref to the actual class to pull back the full instance if I wanted to. So I can execute this map query. So I'll break this query down approximately. So this query, what I'm going to do is I'm going to do a match against the index orders by customer ID. I'm going to look for the customer with the customer ID loan P. The loan P, and so once I get that index back, that returns back a set of data, and then I want to paginate over that set of data. And then it uses a very functional like construct. I'm basically going to map over that set of data and do an operation on that set of data. And the operation I'm going to do is this lambda operation. So what I'm saying is for each item in my list, I want to do get out the order and then basically just return it. So if I run this, this is just going to provide a total list of orders. Right? So I'm mapping over that set of data, and I'm basically just getting the data back and pulling it back. I can also do like get index all orders. Right? So this is going to get me all of the orders out of the database. So this is going to give me a total ordering of all the orders in the database, and then I can actually do operations on that order. In the interest of time, I'm just going to skip a little bit. But essentially what I can do is I can do what's called a let operation. A let is going to take the data set, pull it back out of the database, assign it to a variable, and then I'm going to do an operation on that variable, such as getting the last index out of that order details. Right, so what this is saying is get the last index out of the database, select the 0, 0, which is basically I'm selecting into the row and getting a particular value out of that row. So I got out the value 11110077. So that's the last order ID. And so using that order ID, I can then create a new order that uses that last index. So in this single query, the single let query is going to be a single transaction. This transaction, I'm going to pull that ID back. So basically, I'm reading from the database, pulling that ID in, and then using that ID to create a new order. So if you see down in here, I'm taking the last index, I've assigned it to a variable, and I'm saying, give me the variable last index, add 1 to that index, and then store that as order ID. And so that creates a new order in the database. And that's an entire transaction. So it's doing, it's reading the database, performing some operations on it, and then writing it back down into the database. And it does that all in a transaction. So cool. Time for like 1 or 2 questions really quickly. Cool. Any questions? No? Yeah, go ahead.
I'm not sure if you're familiar, but there's also the Fauna DB that was based on syntax closure. And I wonder if how does it compare with the Fauna DB, because it's also I think really consistent, all temporary. So maybe there's some.
Do you know, Matt, how Atomic DB? Do you know what it uses? Oh, Datomic? Datomic, do you know, Matt, what kind of transaction protocol Datomic is? I don't know either. I don't know what kind of transaction protocol Datomic uses. So, yeah, go ahead.
The DSL that you're using to control this, I guess, what's the closest analog to it?
It's kind of like it's like a functional closure. So it has some similarities to closure, but it's somewhat of a functional language. So I don't know, Matt. What was your inspiration for? Matt might be able to. Matt's the CTO of Fauna. I don't know. What was your inspiration for the Fauna query language, Matt?
It's essentially expression-oriented procedural language. So everything returns result. There's side effects. Maybe like OCaml might be reasonable comparison.
No.
But not much basic syntax.
Cool. That's it. Hey, thank you everyone for coming.